Already we have spoken about Gauss Law, derived the law or established the law, and also have defined what is a Gaussian surface and also different types of continuous charge distributions. Having all these ideas, we can now proceed to apply the Gauss Law in different situations. So where you can apply the Gauss Law to find electric field and then take care of different symmetries that was presented in the representations. The examples are the field of an infinite longer, it represents cylindrical symmetry. Field of a thin sheet of charge, it represents plane, it represents planar charge symmetry of charge, and then field of a uniformly charged sphere, it represents spherical charge symmetry. So, as defined in the earlier video, that different kind of symmetries, we are directly using the Gauss law in this kind of symmetries. So Gauss law has some simplicity, and that's why it's being used in different kind of electricity formulas, in particular to find out electric field. So first, let's take the first example for the case of this cylindrical symmetry. We take as a stated this infinitely long wire, in long wire. So the infinitely long wire is in the form of a cylinder, let's say, and having a radius smaller. And later on we'll observe that this result, whether we are taking a cylinder of a radius A or a very thin, that means A going to 0, will also have the same result. So, let's start with a cylindrical wire of infinite length and having charge capital Q and the length smaller. So, as defined earlier, this lambda is equal to capital Q by L, a linear charge density. And then to calculate the field, we as stated above or in the last video, that we use a Gaussian surface, and Gaussian surface will be passing through the point P, which is the distance smaller from the wire, and the Gaussian surface will have then in that case we have radius smaller and also length smaller. So whenever we use Gauss law to find a field, we use the Gaussian surface concept, and in this case we are using we are making use of Gaussian surface which is passing through the point P, at which we are trying to calculate the electric field. So this is the diagram actually. You can see here that this is the actual wire, and this cylinder is the Gaussian surface, and this Gaussian surface is at a distance r, and we calculate somewhere taking a point P here, suppose, or on this side, that P is here, and at this point P we are calculating the electric field. And the important thing is that this Gaussian surface has a radius smaller, and then it has a length of L. Okay. So this is the diagram we are using, and in this case, as stated earlier, the Gaussian surface is an imaginary surface, but it is very important while calculating the electric field. So coming back to the slide, that now the Gaussian surface would have a area of a spiral impedance. That means the circumference into length of the Gaussian surface. So the Gaussian surface is an area of S given by equation 2. So due to symmetry of the problem, since we know that the flux is equal to some area electric field vector of the area vector, where we come ES cos theta, and the theta determination of theta is very important. So here also we have a theta, and this theta, because you see that the electric field will be radial here because of symmetry, and the curved surface only will contribute, and the end faces will not contribute. Just look at this diagram. Coming back to this diagram, what I understand is that this surface, particular surface, end faces, the electric field direction is this, and the angle is 90 degrees. So this surface, this particular surface will not contribute. Only this curved surface will contribute, just like DS1. But DS2 and DST, this kind of surfaces will not contribute because the angle is 90 degrees. So cos 90 is equal to 1 plus d equal to 0, and that means that flux for these surfaces will be 0, and only the curved surface of the cylindrical Gaussian surface will contribute. So this is because of the symmetry of the problem, and with that we can find that the flux is given to equal to area of the surface S equal to twice pi r L, and then third one is this. And let us now apply Gauss Law, which is given by flux is equal to surface enclosed by the surface divided by epsilon naught, absolute permittivity of free space. So this 1, 2, 3 and 4, and with the help of equation 1 and 2 here, this lambda equal to Q by L, S is equal to twice pi r, and then 3 and 4, we using all this equation 1, 2, 3, 4, we get in expressions like E equal to lambda by twice pi r epsilon naught. So equation 5 gives us the electric field of an infinitely long wire using the Gauss Law. As the idea that you see that this expression 5 is independent of small h. So what is small h? It was the radius of the cylindrical surface. It was the radius of the surface. That means, radius of the cylinder that we took, the real cylinder, since it is independent of A. That means that wherever the value of A, the result of electric field will not change. And if you take a very long, very thick cylinder, the result will be same, or very thin wire, that means the radius is almost 0. Then in that case also the result will be same. So thus the electric field, whether it is a cylinder or a very thin wire, the result will be same. So this is an example of applying Gauss Law regarding cylindrical symmetry. So, and also we find that how the Gaussian surface is very much important while finding the electric field. So this was one example, and just regarding cylindrical symmetry. So let's go for the second one. This is basically related with planar symmetry. So here we take a thin sheet of charge, just like represented by this figure, and this is the thin sheet of charge where the charges are here, and this is the Gaussian surface. And we want to calculate the electric field because of this thin sheet of charge. So we must remember that this thin sheet of charge is the real thing, but the Gaussian surface is imaginary. So with this diagram, you can see that the definitions of sigma, as we know, is equal to Q equal to sigma, because sigma is equal to Q by S. So simplifying it, Q equal to sigma S, surface charge density, and then we calculate the flux now. You can see that the flux for the curved surface is 0 because it is a 90 degree angle with the field as seen in the diagram. So ultimately flux for the coherence is equal to ES minus ES and equal to twice ES. We can understand this form, this diagram. You can see that these end faces as the area vector in this direction, electric field also in the same direction, so angle is 0. So ES cos theta, theta is equal to 0, so this is ES. Similarly here, this has also angle theta, because the S, this area S, has an angle of the area vector representing the surface S is the direction this. So EM this normal to the surface has an angle of theta, so that means it is also S. Since the two directions are opposite, so we put a minus sign, and ultimately this ES and this will add up, and this will have flux of equal flux of what ES plus S twice ES. That's given in this equation number 2. So let's now apply Gauss Law as we have progressed, equal to capital Q epsilon naught, and then using equation 1 to 3 we get twice ES equal to this, and simplifying all these things equal to sigma. So equation 4 gives us the result for a uniform sheet of charge, infinite thin and uniform sheet of charge, which represents an example of planar symmetry of Gaussian surfaces. So in this particular example, if you go back to figure number 2, you can see that here we are using the end faces have only contributed flux because the angle is theta. Theta is equal to 0. But this curved surface, it is an angle of 90 degree, which is electric field. So that's why this particular curved surface has no contribution to the flux. So in the earlier case, the situation opposite, the end faces has no contribution, while the curved surface has a contribution. So let's go for the final application of this Gauss Law. This is required uniformly charged solid sphere. This uniformly charged solid sphere is simply an example of spherical symmetry just discussed in case of Gaussian surfaces. So we have three cases regarding this spherical in case of this solid sphere. The first case is that the electric field will be calculated outside the sphere. The second case will be electric field will be inside the sphere. And the third case will be on the surface of the sphere. So coming back to the case 1, that is outside the sphere, and we consider the figure number 3a. You can see here, this is the figure number 3a, where we are calculating the electric field at the point P, which is outside this solid sphere. This solid sphere is the reality, and this we are drawing again a Gaussian surface for the point P to apply the Gauss law in this corresponding problem. So we can see that this Gaussian surface has a radius of small r and it's a spherical surface. And this is the solid sphere which has a radius of small r. And we are calculating the electric field at a point outside the sphere. So it is obvious that the total charge within the particular sphere is given by capital Q equal to 4 pi s to rho by 3, because here 4 pi a cube by 3 is the volume of that sphere, and as we see here that the Gaussian surface is enclosing the charge enclosed by this sphere. The charge enclosed by this sphere is 4 by t pi a cube to the power pi a to the power 3 into rho. That is, volume of the sphere is equal to 4 by t pi a to the power cube, and rho is the volume charge density. So this is 4 by t pi a cube rho, charge enclosed by this solid sphere. The same charge is also enclosed by this Gaussian surface. That's why we are taking a capital Q is equal to 4 by a cube rho by 3 is given by equation 1. And as in the earlier cases also, here also we are simply drawing the Gaussian surface. In every case we have to do that, and the Gaussian surface is a radius smaller, and as shown in the figure 3a, this is the Gaussian surface. And now let's calculate the flux. The flux will be this, as the defined electric field dot surface area, and since the angle is 0, so it's E naught into S, and S is what? S is the area of the spherical surface. Area of the spherical surface is 4 pi r square. So this is the equation. Here we put a O here. O means outside the sphere. So we are using subscript O, and that's it. Again we are using Gauss law. This is given by equation 3. We know F is equal to capital U by epsilon naught. So we have all these equations 1 to 3. This is 2, this is 3, and 1 was there in the earlier slide. U by this. And 1, 2, 3, all these equations, while combined, would give us this result. E naught equal to 4 pi a cube by rho 3 r square by epsilon. This equation 4 gives us the required result regarding a sphere at a point outside the sphere. So this is the electric field outside a sphere, solid sphere, while using Gauss law, and either with the help of Gaussian surface. So let's go for the case number 2, that inside the sphere there is the same kind of things will be there. Again, you will draw a Gaussian surface. This time the Gaussian surface will be inside the sphere, and you can go back to figure number 3b here. You can see here that this was the solid sphere, and this is the Gaussian surface. Less than this is the Gaussian surface, is also a spherical surface. Again, the radius is small r. Again, you take it. Again, the area of this Gaussian surface will be 4 pi small r square. And our question is that what is the charge enclosed by this Gaussian surface? Obviously, the solid sphere has a larger radius, so it will not be small. So what is that? So definitely we have to find out the volume of this particular enclosed by this Gaussian surface. The volume enclosed by the Gaussian surface is also a spherical thing kind of thing. So this 4 by 3 pi r to the power 2, because this surface has a radius r. So it's not like it's in that case it was 4 by 3 pi a to the power 2, the volume was. But here the volume will be 4 by 3 pi r to the power 2, because the Gaussian surface is enclosing this amount of volume. So this is the very important point. So the charge will be obviously now this 4 pi r to the cube rho by 3. This 4 pi r to the cube by 3 is the volume enclosed by this Gaussian surface. Remember, we have to take the stars that caused by the Gaussian surface, not by the real kind of things. So this is question number 1, and just in the other cases, the flux is this. Now we have got a symbol I here. I means inside a sphere, and so again the volume, the area of the Gaussian surface is S 4 pi r squared. So equation number 2. So in the same line, the Gauss law is this, and this is equal to Q by epsilon naught, and Q by epsilon naught, and then using equation 1 to 3, we get this final answer. U are equal to pi rho r by epsilon. These very simple equations, and we can finally get out the result of the final expressions. So equation 4 again gives us the electric field inside a sphere while using this spherical symmetric spherical solar systems. So let us now go for the case number 6. Very special case, so this is on the surface. To do that, what we have to do that, we just put small r equal to A. That's the thing that we have to do. Small r was the radius of the Gaussian surface, and what was A? A was the radius of the actual solid sphere. So we just put r equal to A, whether equation 4 in case of outside the sphere or whether in case of equation 4 in case of inside the sphere. So putting all these things, we get results like this. E is equal to then r equal to A, and this equation we get 4 pi OA by 3 epsilon naught. As I am talking about this expression actually. This expression, I am talking about equation 4. In this expression we put r equal to A, and we will get this equation. Pi OA by 3 epsilon naught. Very simple this, and then we then take this equation, this is in case of inside the sphere. We get put here r equal to A corresponding to the surface. Again, the same result will be obtained. You can see here. Yes, the same result is there. So this particular video is consisting of the applications of Gauss law, regarding cylindrical symmetry, regarding planar symmetry, and regarding spherical symmetry. In all applications, we see that the Gaussian surface concept is very important. We have to draw a Gaussian surface, and that Gaussian surface will decide the flux actually, and we have to take the angle very carefully, the theta, while calculating the flux, because velocity is very important, and which surface is actually contributing the flux, that will depend on that particular angle. So we have ultimately this self-assessment while the Gaussian surface, and then this kind of different applications for a planar symmetry, that in case of infinitely long cylindrical wire, and then spherical symmetry in case of the solid sphere, and then cylindrical symmetry. That means the third one is in case of planar symmetry. Let me say. So these are certain things that you can do with the help of this video. Planar symmetry, that means thin sheet of stars. Spherical symmetry, the solid sphere case, and cylindrical symmetry, that infinitely long cylindrical wire. So to conclude that this particular video shows you the application of Gauss law in relation to different kind of symmetries, all symmetries, cylindrical symmetries, planar symmetries, and as well as spherical symmetries. I hope that the video is helpful for you, and